Good morning, good evening. We have chosen to do SCUDEM problem C, dog cannot catch.
I'm Cadet Lucas Sorensen.
I'm Cadet Madeleine Rygh.
And I'm Cadet Elijah Goodwin. We are from the United States Military Academy in West Point, New York. Our coach is Major Devon Zillmer. Our team number is 1111 and the date is 13 November 2023.
In the context of this scenario, an owner is throwing various treats at a dog named Fritz while outside. From the videos that are provided to us, it is very apparent that Fritz is unable to catch the majority of treats that are thrown at him. He drops the majority of his treats. To decide whether this is Fritz's fault, which means that Fritz is unable to follow the projectile motion of the treat, or the owner's fault, which means that the owner is either bad at throwing treats or the owner purposely misthrows the treats in order to gain social media likes off of Fritz. We decided to model the system of equations in 3D space. So we modeled this in X, Y, and Z direction. We additionally incorporated a learning curve as we figured out to make our model more accurate as Fritz is a dog able to learn. To further develop our model and make it more accurate and lifelike, we decided to add some assumptions. Our first assumption is that Fritz and the owner remain fixed in place, which means that neither Fritz nor the owner moves significantly after after the treat is thrown. And then our second assumption for that is that Fritz has a defined range that he can catch the treat in. We also will assume that there is drag due to the density and cross-sectional area of the treat, which employs the physics of our situation and creates our situation to be more lifelike. We also assume that the net force on the treat is constant, meaning that there are no varying forces that are being applied to the treat. And then lastly, we also assume that the treat maintains a stable orientation or a mostly stable orientation. As in the videos that are provided, we can see that the treats do not majorly change their orientation and have minimal orientation movement.
These last two assumptions were also made to simplify the equations being produced, as a cross-sectional area that stays constant is much easier to model. Similarly, a net force that is constant is much easier to model. Furthermore, we can see there's no wind in the video affecting the trajectory of these projectiles.
In order to construct our model, we first need to define our parameters. Our first parameter is t. T is the time in seconds since the treat left the owner's hand. X of t, y of t, and z of t are the displacement of the treat in the x, y, and z directions. M is the mass of the treat in kilograms. C is the drag coefficient. A is the cross-sectional area of the treat. G is gravity, which is negative 9.8 meters per second squared. Rho is the density of air, which is 1.2 kilograms per meters cubed. V naught is the initial velocity in meters per second, and theta is the angle that the treat is thrown at, broken down into x, y, and z directions. To define the cross-sectional area, we made this table that provides us with a cross-sectional area of many of the different shapes that our treats are being thrown at. So we have the cross-sectional area of a sphere, which is meant to model the cross-sectional area of the meatball we've seen being thrown at Fritz. We have the cross-sectional area of a triangle, which models the pizza that is thrown at Fritz. The cube, which models the tofu. The rectangle, which models the steak. And the teardrop, which models the almond. The reason that we included these parameters for the cross-sectional area is to establish a more accurate projectile motion for the treats through accounting for their difference in cross-sectional area.
To better understand our problem and to create a model of the projectile's trajectory, we created three second-order differential equations, as well as defining net force, which is a function of mass and gravity, as well as 1/2 rho AC velocity squared, where rho is the density of air and A is air resistance, with a big emphasis on the cross-sectional area, as that is what changes with each object being thrown. Furthermore, we have the x, y, and z directions, which are functions of mass times the respective second-order differential equation, which is this long function which determines the angle at which the object is thrown, the initial velocity, as well as the net force, with a change in these second-order differential equations in the y direction, which has to account for gravity and the mass of the object in order to properly model the trajectory it takes. These three equations were derived from these two free body diagrams, where we can see that velocity is counteracted by air resistance, and the mass of an object can greatly determine the trajectory it takes.
Some other important takeaways of this is that from these equations, our model outputs a velocity vector in the x, y, and z directions, and a time that it takes to reach the destination, which is Fritz's height.
Modeling these three equations, we get this diagram, which shows the white trajectory, which is the trajectory Fritz believes the object will take, and the red, which is the actual trajectory, with this cylinder being a model of Fritz. As we can see, Fritz only has 0.864 seconds to react by the time the treat hits him, which could partially explain why he's so bad at catching treats.
Obviously, 0.864 seconds is a very short amount of time for Fritz to react, which is why we begin to conclude that Fritz isn't necessarily being treated unfairly. He is just not that great at catching the treats yet.
Looking further at this diagram and putting the 3D perspective, we can see this cylinder has a circle on top which represents the area that Fritz can reasonably get to catch the object in time. As we can see, the red, the actual trajectory the object should be taking, lands directly on this circle, showing that Fritz can and should be able to catch it. However, as he believes the white is the actual trajectory, he jumps to try to get it, resulting in the red hitting prematurely instead of where he actually is.
We must also recognize that from the videos, the owner does generally throw the treat in this area, the top of the sphere or the cylinder, which leads us to believe once again that Fritz is not being treated unfairly, and he is just simply misinterpreting maybe something like the initial velocity, the throw angles, the height that it's thrown, all those different factors.
As Elijah said, Fritz is treated quite fairly. As we can see from these photos, the treat hits Fritz directly where his mouth should be. However, he orients himself improperly, oftentimes looking up, believing that the treat will go higher, resulting in a miscatch. Furthermore, he might try to orient himself differently, which once again results in him not being able to catch the treat, or he simply does not have enough time to react and simply does not move. From these conclusions, we have arrived at the fact that Fritz is simply bad at catching treats and the owner is not at fault.
If Fritz continues to stay in a relatively still position and tries not to intercept the treat and practices and learns better, we believe that he will have a better time catching the treats. To talk about this learning curve, we will introduce the base model of a learning curve as a first order differential. dl over dt equal to k, which is a proportionality, times the L max minus the L. And L, in this case, is a unitless measure of learning capability or knowledge. L max is representative of Fritz knowing 100% of the time where the treat will be, where to place himself, and how to catch it. Through some manipulation, we're able to turn this into this final equation where L of t, the learning capability, is equal to the L max, which is 100, times the L max minus m times e to the negative kt. We found m when c is equal to L of 0. And L of 0 in this context ends up being equal to the L max minus the m, where the m is the initial knowledge of Fritz. And in this context, Fritz has little to no knowledge of how to catch these treats, seeing as he misses almost every single one. To visually represent this model, we're left with this graph. So what we can see as time in days passes, Fritz's knowledge increases. However, it is not a linear relationship and rather a more exponential curve. So we can see that around 65 to 70 days, Fritz's knowledge really picks up and he starts to get better and better at catching these treats and figuring out what comes into catching it. So from this, we can begin to say that Fritz simply needs to practice consistently at catching these treats to get better. The owner is not unfairly treating Fritz, And if the owner wants to help Fritz out, he should practice with him every day, very intentionally, throwing the treat in the same general area like he usually does. And from our graph, we can see that around time 100 days, Fritz will be almost perfect at catching these treats. And here is our citation slide. Thank you very much for watching.